The James Webb Space Telescope just captured something extraordinary. A star exploding when the universe was only 730 million years old. This isn't just the most distant supernova ever directly observed. It's a window into how the first generations of stars lived and died during the cosmic dawn. March 14, 2025. The alert came from SVOM, the space-based multi-band astronomical variable objects monitor, a Franco-Chinese satellite designed to catch fleeting cosmic events. A powerful flash of high-energy radiation, a long-duration gamma-ray burst lasting about 10 seconds. These bursts are among the most energetic events in the universe, often linked to the catastrophic collapse of massive stars. Within an hour and a half, NASA's Neil Gehrels Swift Observatory pinpointed the X-ray source's location. 11 hours later, the Nordic Optical Telescope in the Canary Islands detected an infrared afterglow, a sign that this might be an extremely distant object. 4 hours after that, the European Southern Observatory's Very Large Telescope in Chile measured the distance, 730 million years after the Big Bang, deep in the era of Reionization, when the first stars and galaxies were emerging and transforming the infant universe. The event was catalogued as GRB 250314A, but gamma-ray bursts are brief, just seconds to minutes. To confirm it was a supernova, astronomers needed more data. About 110 days later, the James Webb Space Telescope turned its near-infrared camera toward the same patch of sky. By then, the afterglow had faded. But Webb detected something else, an extra glow that couldn't be explained by the afterglow or the faint host galaxy alone. It was the supernova, the explosive death of a massive star, captured 13 billion light-years away. The key observation, or smoking gun, that connects the death of massive stars with gamma-ray bursts is the discovery of a supernova emerging at the same sky location, said Dr. Antonio Martin Carrillo, co-author and astrophysicist at University College Dublin. Here's where it gets fascinating, quote. Using models based on local supernovae associated with gamma-ray bursts, the team made predictions about what this ancient explosion should look like. To our surprise, our model worked remarkably well, and the observed supernova seems to match really well the death of stars that we see regularly, Martin Carrillo explained. The distant supernova is strikingly similar in brightness and spectral properties to SN 1998BW, a well-studied supernova from the local universe that exploded in association with a gamma-ray burst. This was unexpected. Many models suggested that the first generations of stars, born in nearly pristine gas with very low metallicity, should be more massive, more unusual, and should produce brighter or bluer explosions than the stars we see today. But GRB 2503b14A suggests otherwise. At least some massive stars in the early universe behaved much like the massive stars we observe now. They lived fast, died young, and exploded in similar ways, despite the vastly different physical conditions of the infant cosmos. These results challenge the long-held idea that the earliest stars would produce explosions that were distinctly brighter or bluer than those seen today, the researchers noted. Instead, the findings point to a surprising consistency in how massive stars end their lives across cosmic time. Webb also delivered the first clear glimpse of the host galaxy, a compact star-forming system typical of the Reionization epoch. The galaxy appears as a reddened smudge, its light blended into just a few pixels. What we can learn about it is still limited, but seeing it at all is a breakthrough. Webb's observations indicate that this distant galaxy is similar to other galaxies that existed at the same time, said Aymeric Lefloc, co-author and astronomer at CEA Paris-Saclay in France. This discovery provides a direct look at the violent death of a massive star from a time when the universe was just beginning to light up It confirms that at least some early stars followed familiar patterns, seeding space with heavy elements that would eventually allow later generations of stars and planets and life to form. It also demonstrates Webb's power to capture events at the edge of observability. Gamma-ray bursts are brief, supernovae fade quickly. The host galaxies are incredibly faint, but Webb can separate these contributions and isolate the signal of the exploding star itself. The research team has already been approved for follow-up observations. In the next 1 to 2 years, they'll observe the same region again after the supernova has faded by more than 2 magnitudes. That will allow them to fully characterize the faint host galaxy, confirm the supernova's contribution, and potentially learn more about the environment where this ancient star died. Lead author Andrew Levin noted that the team now has a new goal: to learn more about distant galaxies by capturing the afterglows of gamma-ray bursts themselves. That glow will help Webb see more and give us a fingerprint of the galaxy, Levin said. GRB 250314A now holds the record for the most distant confirmed supernova, beating the previous record holder that exploded when the universe was already 1.8 billion years old. By capturing this explosion so close to the beginning of time, Webb has opened a new window on how the universe built the chemistry that later allowed life to emerge. Future gamma-ray bursts and follow-up observations will show whether this ancient star was typical or an outlier. For now, GRB 250314A stands as a reminder that even in the universe's youth, stars were already living fast, dying young, and seeding space with the building blocks of future worlds. Like, share, and subscribe for more cosmic discoveries, and as always, keep looking up.